Hello again. In this lesson, we're going to expand on our understanding of displacement mapping. So we've already established that displacement mapping is the displacement of vertices based on the information stored in a 2D image. What we haven't said so far is that the vertices can only be displaced in the direction of their vertex normal, and that these displacements can be negative as well as positive. Let's bring up the 2D image that represents our displacement in Photoshop to see how these negative and positive values are achieved. You can find this image in the Lesson 3 folder. Incidentally, images like this that are used to store information are called height maps, or when they're used for the purposes of displacement mapping, are referred to as displacement maps. So how does this work then? Well, the color intensity of each individual pixel of our displacement map represents the intensity of displacement of the corresponding vertex that is mapped to that pixel. This middle gray here is used to represent no displacement. Any areas which are lighter than that, such as this middle part here, or any of these knobs around the edge, represent positive displacement. Conversely, any areas which are darker than the middle grey, such as these slats here, or even darker still, these slits, represent negative displacement. Let's quickly get Photoshop and Marmoset up side by side on the screen so we can see how this translates to our shield. Let's just push Photoshop across there, hide this menu, pull Marmoset down here, and quickly rotate our shield to about there. So what we're going to do in a second is, using the displacement widget just here, is drop the displacement scale down to 0 before slowly bringing it back up. Whilst we do this, I want you to pay attention to the direction of the displacement of our vertices. Okay, so let's go ahead and drop the scale down to 0. Then bring it slowly back up to about there. Right, so what we should have seen is that for these darker areas of our displacement map, the areas that we said were indicative of negative displacement, the vertices were displaced inwards into the shield. Whereas in the lighter areas, the vertices were displaced outwards or away from the shield. So we've seen how displacement occurs on these front faces, where the vertex normals are in the exact same direction. But let's talk a bit about the areas that have less uniform vertex normals. Let's make Marmoset full screen again, take the displacement scale back down to 0, and zoom in on this area of the model here. Now, so we can see this a little clearer, let's go over to the Render tab and turn our wireframe on. This time, as we increase the displacement scale, pay attention to the vertices along these edges. As you saw, these vertices were not displaced at all. Instead, the vertices on these top faces were used to form the curve of our shield. Now this is all to do with the direction of our vertex normals. So if we take the displacement scale down again, these vertices on this edge here will have vertex normals which are roughly in this direction. Therefore, when the displacement occurs, they are not used to form the curve because their vertex normals are in the wrong direction. So the vertices on the top faces are used instead because their vertex normals are closer to the direction which is required to form the curve. Right, with that covered, we can now move on to the first misconception surrounding displacement mapping. In games, normal maps are the standard method used to create the illusion of surface detail on a model. However, since the advent of displacement mapping, which, along with tessellation, is used to physically create this detail, there has been speculation as to whether normal maps are still required. The answer to this is absolutely. To understand why, let's zoom back out on our shield and rotate it till about there. We'll also need to turn our wireframe off and put our displacement scale back up. Now let's go down to the surface widget here, where we'll already have a normal map applied to our shield. To remove it, we just need to click this X. Once we've done that, we'll see that the displacement of our shield will look like it has also been removed. However, if we rotate the shield 90 degrees, we can see that the displacement mapping is still working, but we just can't see it clearly. The reason for this is that displacement mapping only displaces the vertices. It does not alter their vertex normals to correspond with their new positions. Because of this, if anything, normal maps are even more crucial for displacement mapping to work properly. In this lesson, we went into more detail about displacement mapping, how the vertices are displaced, and why we need normal maps. In the next lesson, we'll start to learn how displacement maps are generated.